Hello everyone. We have been talking about Born rule in the last few lectures. So let me just give you a reminder of what was that. Let's say I have a quantum system which is, let's say, in some basis I could write it like this: A1 E1 plus A2 E2 plus A3 E3. All right. And then the Born rule was, if you do a measurement, the probability of getting the state EI is equal to the probability is EI psi mod square. All right. So if this is an orthogonal basis, let's say the probability of getting E1 will be taking an inner product with all of these, and E1 inner product with E2 and E3 will give you 0. So what you'll be left with is just A1 square. All right. So probability of getting E1 was modulus of A1 square, and similarly you can calculate the rest, right? This was Born rule. And your collapse state, new collapsed state was E1, and as it was normalized, it was a normalized basis, so I mean it was A1 E1 divided by square root of probability of getting E1, right? If you divide it by this, then you get the normalized state, which is E1. All right. So this was the idea for regular Born rule, and now we will talk about the extended Born rule. So the idea is almost similar. What we will do now, let's say that I have a multiple qubit system. Let's say I have a composite system of S1 and S2. All right, so it can be like a multi-qubit system. And let's say they belong to, they form a vector space, which is V tensor W. All right. And let's say that this V has a orthonormal basis set like this: E1, E2 up till En. All right. So now any state psi of this composite system can be written as something like this: sum over I, and you can write EI, and you will have some xi. This is a Greek letter xi I. All right. So what does it mean? If you remember correctly, that two qubit systems can be written in this basis: 0 0 plus let's say it's 1 by root 2 plus 1 by root 2 0 1. Let's say that. All right, but this is a state in a two qubit system. So if you write it like this, 1 by square sorry, let me just write it properly. So I can write it as 0 times 1 by square root of 2 0 plus 1 by square root of 2 1. This is the second qubit part in the parenthesis. So what you're left with, so this is like your xi, and this is your EI here. I mean, I'm comparing these two. All right. So this is how it looks like. I can write a multiple qubit, I mean a composite system like this equation. Okay. And now I can also think of it like, so what is my xi I? Okay, I can also think of it as something like this: sum over ij, aij, and this is ei, and this is fj, where fj's are the basis of this W space. If I say that the basis of this is F1 up till F whatever, it can be like Fm. Okay, so from here I can see that let me use a different color. So here I can see that xi I can be written as sum over j a I j f j, right? So this is the idea, that I can write a composite system in this way, and I can also clearly see that I can write from this equation, this one, from this equation we can say that our xi I is equal to inner product EI times psi, right? Because EI was an orthonormal basis, so if you take an inner product in this side, if you take an inner product in this side, only one term out of this sum will survive, and that will be this one. All right, so this is how we can see this equation. So now what is the Born rule? Now let's try to understand what it says. So if you perform a measurement in the first system, that means that you just perform a measurement in this V space and you do not touch the second one. That means that if you have like 2 quantum bits or 2 qubits, then you just perform a measurement in the first one and then you leave the second one. Then what's the associated probability of getting everything, right? So that's the idea. So we do a partial measurement. So we have this V tensor W space, and we want to perform a measurement, in the basis, this one, E1 up till En, in the V slot. Okay, so what happens? So let's check it out and let's look at this. It will be easier if I work out with an example with you. That will be easy for you to look at it. Okay, so let's say psi, and this E1, and I just have 2 terms. Let's say I have E1 xi1 plus E2 xi2. I'm just working out this example because it will be easier for you to understand, so I don't have to write the sums and everything every time. All right, so the probability, so if you do a measurement in this spaces, in this E basis, then what you get, the probability, so the Born rule 1 is probability of getting E1 is, let's write it like this, probability of getting 1 is equal to the mod square of this state xi1, mod xi1. All right, so you can see it's similar because previously, if you look at this, the probability of getting E1 here, okay, let me use a different color. The probability of getting E1 was just the mod square of whatever you have here, right? In the same sense, the probability of getting E1 here is the mod square of whatever you have here, and which is a state now rather than a complex number. All right, or you can look at it as I showed it here, that psi I is just the inner product of psi with ei, then what I can write is that this can be equal to mod square of E1 psi. Alright, because you can see that if you take this inner product of psi with E1, you just get that psi. So it's the same thing. So this is something we got here as well, this line. Okay, so this is the probability. And now what is the idea of getting the collapse state, right? So, and okay, and I think you can easily calculate probability of 2. The probability of 2 will be just giving all 2's here. All right, now let's say that what will be the collapse state. So this was the probability. The collapse state, post measurement state, post measurement state will be psi after, let's call this psi after, will be, if you collapse to 1, then this will be E1 psi 1, but psi 1 is not necessarily normalized, right? So we have to divide. So whenever you have a vector, if you want to normalize it, you have to divide by its norm, right? By its mod square. And E1 is already a unit vector. So if you wanted to calculate the norm of this vector, you just have to take this psi. All right, and this is nothing but yes, this is the oh, I made a mistake, the square root of this number, right? The square root of the norm, then you get that. So the new state will be E1 psi 1, and you have this square root of the probability of 1, right? If you're confused with the square root, then let me give you an example that if you have some vector A and you want to normalize it, you have to divide by the modulus, right? And how do you calculate the modulus? You calculate the modulus with the square root of A dot A, right? So this thing is like A dot A, and then you have to take the square root. All right, so this is the idea. So if I want to summarize, then if you have a composite system like this, then you can write it as a sum over Ei and Xi I. And if you perform a measurement in the first vector space, which is the V space, that as we are calling it, then the probability of getting some Ei will be the inner product between Xi I and Xi I. And you can calculate, you can analogously calculate it for I. And the post measurement state will be a product state of Ei times Xi, all right? And it will be normalized by the norm, by the square root of the norm square. All right. So this is the idea, and this is the extended Born rule, and we will be using this idea for multiple qubit systems, and we will be performing partial measurements. So I will work out an example in the next video, and I hope it will be clear to you. Thank you.